Our next topic, 9.7, is called Taylor and Maclaurin Polynomials. This is the only topic that Delta Math actually includes in their curriculum, and I actually like that because I'm going to run you through some of the Delta Math ones that I think seeing it on that platform actually will make this make a little more sense. It's probably still going to seem kind of useless and not super exciting, but hopefully at least will be more understandable. So a Taylor or a Maclaurin polynomial, what they are polynomials. They are power-based functions, so things taken to a power that approximate a more complex function. So a lot of the functions we'll be looking at are things like trig functions, natural log functions, exponential functions that are very difficult to work with by hand. And so we look at polynomials like x cubed plus x squared, something like that, that are much easier to work with. So it's taking something more complex and finding a way to write it in a more simplistic form that approximates it. So we have a couple definitions here. We have the nth Taylor polynomial, and the n stands for derivatives. So nth is the number of derivatives taken at a c value. C is still the center. Then to write the Taylor polynomial, you can kind of look at this, and at first it's going to look like a big mess, but there's actually a pattern that develops here. So to get your terms of your polynomial, your first term is going to be what you get when you put the center into your original function. So if your original function is a natural log and you're centered at 2, you'll just put 2 into that. Your second term in your polynomial is going to be what you get when you put the c value into the derivative of the original function. And then you're going to be taking that times x minus the center. Then the next term is putting it into the second derivative of the function, dividing it by 2 factorial, which is just 2 times 1, times x minus the center squared. And then the pattern continues. You'll do the third derivative, plugging that value in over the third factorial times the third power of x minus c. And then if there was another term, it would be the fourth derivative divided by 4 factorial times x minus c to the fourth power. And you keep going however many numbers of derivatives they want you to take until you get this polynomial. The bigger the polynomial, the more derivatives you take, the better the approximation will be. So I'm going to walk you through how to do some of these, but that's kind of how we build this polynomial. And what I love in Delta Math is they actually do it step by step with you, so you can see kind of how we build it by taking derivatives and plugging things in and seeing what I get. We also have something called a Maclaurin polynomial. So in my mind, Taylor and Maclaurin were both mathematicians back in, I think it was the early 1800s, and they didn't work together. But Taylor and Maclaurin both get known for working with the same idea of mathematics. But it's funny because Maclaurin's polynomial is basically saying, what if we did everything Taylor did, but we made our center 0? I have no idea why he gets his name in all the textbooks for doing nothing more than saying, let's just plug 0 in everywhere. But that's essentially what he did. I do want a McPherson polynomial. I would center it like 3 because I really like 3. But all he's doing with his polynomial is saying, well, now I'm just going to put 0 into my function. Then I'm going to put 0 into the derivative times x. Then I'm going to put 0 into the second derivative times x squared over 2 factorial, and continuing that pattern. The one thing I do want you to realize is if you're reading a question on a test and it says write a Maclaurin polynomial, immediately you need to think, okay, my center is 0. If it doesn't say Maclaurin, they have to tell you the center. So they would have to say I'm centered at 2 or 1 or 5 or a different value. So I'm going to show you a really basic one first, and then I'm going to go to Delta Math because I think they actually do a really good job of helping students build this. So this one is asking you to write a Maclaurin polynomial for e to the x out to 4 derivatives. So this n is representing the number of derivatives that you need to take. So to do this question, what I like to do is I just like to make a list of my original function and all the derivatives. Well, the beautiful thing about this one is every derivative of e to the x is still e to the x. So we are still getting, if we go out, takes me a second just to catch up with the writing. Go out 3 derivatives, we still get e to the x, and go out 4 derivatives. If you go to a derivative higher than 3, you will see the derivative number in parentheses, e to the x. And then I need to figure out what happens when I put the center, which in this case is 0 because it is a Maclaurin, into all of these values. Well, when I put 0 in for all of these, I'm going to get e to the 0, which is 1. So I'm going to get 1 for every single plug-in of 0 into every level of the derivative. So this polynomial is going to be really easy to write. It is going to be my first constant term, all by itself, plus my second constant term, which is 1, times x to the first power. So it's just going to be 1x. And then my next one is going to be 1x squared over 2 factorial, or you could just write 2. And then my next one is going to be 1 times x cubed over 3 factorial. 3 factorial is also 6, 3 times 2 times 1. And then my last one is going to be x to the 4th over 4 factorial. Here's what you found, and it does not seem that exciting in the age of technology and graphing calculators and everything we can do. But this polynomial will be an excellent way to approximate e to the x anywhere that's near the center. So for example, if I use this polynomial, so I'm going to call this, instead of f of x so I don't confuse it, I'm going to just call it like p sub 4, so it's the 4th one. If I want to figure out what happens when I plug in, let's say I want to plug in 0.1 for x. Hold on. 0.1, sorry. If I want to put 0.1 in for x. So if I go to this polynomial and everywhere I see an x, I plug in 0.1. So I'll have 1 plus 0.1 plus 0.1 squared over 2 plus 0.1 cubed over 3 factorial plus 0.1 to the 4th. I end up, so when I put 0.1 in there, I end up getting a decimal on my calculator of about 1.105, and it keeps going 170. If I want to see what happens with my original function at 0.1, so my e to the x, e at 0.1, if you go to your calculator, e at 0.1, e to the 0.1 power, is 1.105170, and so on. It's almost identical. So that's what this polynomial is doing. It's giving you a polynomial that is not exponential anymore, something that's a little more simplistic, although it can get very long, to make an approximation that is near the center. The closer to the center, the better the approximation. If I try to make an approximation far away from the center, it's not going to be very good. So if I stick close, in this case my center is 0, if I pick x values to plug in that are close to 0, we're going to have a really great approximation. And as I deviate away from that center, I'm going to weaken my approximation. So let me show you how Delta Math does it. So Delta Math has a couple sections, and I want you to specifically look at these ones that are called guided Taylor polynomials. So they're going to give you a function. Trig, ease, natural log seem to be their go-to, and it's going to ask you how many, it's going to tell you what degree, so degree is your exponent, like how many exponents you're going to have. And to do this, it's going to guide you in the direction of, here's my original function, what do I get when I derive it, what do I get when I derive it again. So I'm just going to type this in. So my original function is -4 cosine of 2x. The derivative of that, all right, so the derivative of cosine is negative, but it's already negative. So I get a sine. And then I also have to derive the angle. When I derive the angle, I get 2. So I'm going to get 8 sine 2x. When I derive it again, the derivative of sine is just positive cosine. I also have to derive the angle. So I'm going to get 16 cosine 2x, my angle, not 12x, 2x. When I derive a third time, it's going to go back to negative. It's going to be -32 sine 2x. And then when I derive it one more time, derivative of sine is cosine. It's going to stay negative. I'm going to multiply by the 2, so I get -64 cosine 2x. So it's going to ask you to fill in as many derivatives as whatever they're asking you to do. If we're doing a 4th degree, we know we need to get to 4 derivatives. So I have my original function and my 4 derivatives. Then it's going to ask you to plug in your center value. This is a Maclaurin polynomial, so we're centered at 0. So when I put 0 in, let's see, the cosine of 0 is 1. So I'm going to get -4 when I put 0 into the original. When I put 0 in, the sine of 0 is 0. So I'm going to get 0 for that one. My cosine of 0 is 1, so I'm going to get just 16 times 1, or 16. Sine of 0 is still 0. Cosine of 0 is still 1, so -64. So first it's going to ask you to fill in this chart, all your derivatives and all your values at the center of those derivatives. For some reason, I don't know why it looks like this. I'm going to go to try, and it's going to then ask you to write that 4th degree polynomial using the information that's up above. So my first term is going to be -4. My first term, there's no derivative, there's no x, it's just -4. My second term is actually 0, so I don't need to write that one down. So I'm going to skip the first derivative, and I'm going to go to the second derivative. This one is going to be plus 16. Since it's a second derivative, it's going to be divided by the second factorial. So it's going to be divided by 2 factorial, or just 2. And then it's going to be x minus the center, which is just x, to the second power. So you're going to have an x squared. A little while to type in, although it's faster to type it in than it is to write these. My next term is going to be 0, so I will not have a third derivative, a third power, a third factorial. So I'm going to jump to the fourth one. I get a negative 64 divided by 4 factorial. 4 factorial, 4 times 3 times 2 times 1 is 24. And then x to the fourth. So there's my polynomial. You'll notice it doesn't have as many terms because we had so many 0 terms. Here's what it does. It's going to take my original function, which is the negative 4 cosine 2x, and that's actually like the dotted line, and it's going to draw my 4th degree polynomial in a solid red. And what you'll notice is at the center, so at 0, they have the exact same value. But even as you go a little bit to the left of 0 and a little bit to the right of 0, this path of this polynomial, the red curve, is almost identical to the dotted line, which is the cosine. So that's the approximation that's made. I believe you do have to hit try one more time, and then it asks you to submit. And there you go. And it will show you all the different values, what you get when you plug in, and it will even show you a picture, that's something I can't do by hand. I'm going to show you one more just so you get to see one more. I don't want to do a trig one. I want to do something different. Let's do an E one. So with our E ones, so this one wants a 5th degree polynomial, so I'm going to have to go out and derive 5 times, but they'll give you 5 boxes for that. E's are very easy to derive multiple times. In this case, every time I derive, I'm going to multiply by a negative 5 because of that exponent. So my original one is e to the negative 5x. My first derivative is going to be negative 5 e to the negative 5x. My next derivative is going to end up positive 25 e to the negative 5x. My next one is going to be negative, I'm going to eventually need a calculator here, I think, e to the negative 5x. Next one, okay, I'm testing the ability of my math here. So that's 625 e to the negative 5x. Oh boy, all right, I'm going to a calculator. 625 times 5. 3,125. This one's going to be negative 3,125 e to the negative 5x. So you've got all your polynomials. This again is a Maclaurin, which means we're putting 0 in. That's your center. It does remind you that you need x equals 0. All right, so when I put 0 in, e to the 0 is 1. So my first term is just going to be a 1. My second term is just going to be a negative 5. All the e pieces are going to be 1. My next term is going to be 25 when I put 0 in, then negative 125, then 625, and negative 3,125. Try. What they'll give you is this is a picture of e to the negative 5x. So that's what they start out. And they're going to ask you to write out this big polynomial. And as you write it out, it's going to kind of show you the graph that's forming. So my first term is just 1. And then my second term is going to be a negative 5. And then it's going to be x to the first power. And then my next term is going to be 25. I wanted 25. It's going to be divided by 2 factorial, or just divided by 2. And it's going to be x to the second power. As you go, you can kind of see it keeps changing the picture here. Then my next one is going to be negative 125. Negative 125. That's going to be divided by 3 factorial, which I'm just going to put in as a 6. And then x to the third power. And then my next one is 625. 625 divided by 4 factorial, which is 24, x to the fourth. And then finally, negative 3,125 divided by 5 factorial. 5 times 4 times 3 times 2 times 1 is 120. You're welcome to use a calculator. I don't even know if you can just type in the factorial key. I'm not really sure. Haven't tried it. So there's my polynomial, and look how closely it models until we get away from the center. You'll notice once here, like this curve keeps going flat, this curve goes through the axis, but it's a perfect approximation at the center of 0, and it's a really good approximation right before and right after 0. I think I've got everything. I don't know why it asks you to hit try a couple times, but it won't let you continue until you do. And there you go. There's all the values, all the derivatives, plugging it in, and then the picture that I saw. So that gives you an overview of Taylor polynomials. I wish I could say they were super exciting, but I think Delta Math makes them so much easier to actually put together and build. You won't build a lot of these because they can be very time consuming.